Hello, and welcome to today's WJE webinar. My name is Liz Pimper, and I'll be your moderator for this webinar, Advances in Ultra-High Performance Concrete. During the next hour, WJE materials engineers John Lawler and Elizabeth Nadelman will provide an overview of UHPC, including its constituent materials, mixture proportioning, and production processes, focusing on key differences between UHPC and conventional and high-performance concretes, as well as on current and future uses of UHPC in architectural and structural applications. And now I will turn it over to John to get us started. John?
Hello, everybody. I'm John Lawler from WJE's Janney Technical Center Laboratories in Northbrook, Illinois. I'll be talking today with my colleague, Elizabeth Nadelman, also here at WJE's lab. And obviously, the topic of the discussion today is ultra-high performance concrete, or UHPC. So we've had more than 300 people register for this webinar, and based on this registration, we recognize that we're talking to structural and materials engineers, construction managers, architects, and some other folks. Our goal is to provide something of interest for each of the people here in the audience. Overall, the intent of our discussion today is to provide you a sense of what UHPC is, how it's produced, and where it can be used effectively. To that end, when we finish this presentation, you should be able to describe characteristics of UHPC and compare those characteristics to conventional concrete. You should also have an understanding of current applications of UHPC and be able to discuss some of the future directions that the technology is headed in. So here's the outline of today's presentation. We'll start by talking about what UHPC is, then get into UHPC mixtures, proportioning, and development of those mixtures. We'll talk about production of UHPC, as well as some current UHPC applications, and then, as I said, some of the future of UHPC. The presentation may get a little technical at times, but I hope you stick it through to the end, because we'll come back to kind of summarize some ideas as to when and how UHPC can best be used for your individual work. All right, so before we get into UHPC, I want to take a step back and start with some of the basic concepts regarding the use of concrete. The intent of the first couple slides that we're going to share here is not to show you something that you already know, but really to kind of illustrate that UHPC is just a natural evolution in the use of concrete. So to start at the beginning, early last century, it was recognized that a low water cement ratio produces a dense concrete. And that greater density gives us higher strength and lower permeability, good things for concrete. But there's a consequence there, and the limitation is workability. If you don't have enough water, the concrete just doesn't flow. In the 1970s or so, through the introduction of water-reducing admixtures or superplasticizers, we were able to lower that water cement ratio and still get that flow. The density of the concrete was improved even further by the incorporation of silica fume, which largely became commercialized at about this time. The combination of the low water cement ratio and the silica fume allowed very high strength concretes to be achieved relatively easily. However, pretty quickly after some laboratory work looking at the combination of the low water cement ratio and silica fume, there was a recognition that, hey, maybe that wasn't as good as it might seem, because there was a greater risk of cracking, which ultimately would compromise the durability of the structure. So moving beyond that, what was developed was an understanding that using other supplementary cementitious materials like fly ash, you could balance some of the effects of the silica fume while still taking advantage of the benefits of the low water cement ratio. At about this time, the term high performance concrete was coined to distinguish this type of concrete from the high strength concrete that had been used previously, where kind of by definition, high performance concrete was specifically focused on a certain property, such as durability. So then the next step along this process is really the development of now ultra high performance concrete. What we're doing here is getting an ultra low water cement ratio, again through high dosages of superplasticizer. The elimination of coarse aggregate from the mix, as well as the introduction of supplemental materials, allowed for a focus on particle packing, As we'll talk about a little bit more later in this presentation, the idea behind particle packing is to really maximize the density of our material, and there's performance benefits associated with that we'll get into. Another characteristic of the ultra-high performance concrete is the introduction of fibers, and those introduce tensile properties that can be relied on, and again, I'll get into that a little bit more. So as you can see from our timeline here, ultra-high performance concrete's been around since the 90s, but to date, it's seen limited implementation, and that's largely because of a high cost, and also as a result of a lack of specifications and design guidelines. But that's starting to change, and again, we'll kind of come back to that as we go through this. So, kind of summarizing that, what is ultra-high performance concrete? Well, it is a fiber-reinforced cementitious composite with a low water-cement ratio. But most of the materials that are incorporated in UHPC are the same as we use in conventional and high-performance concretes. So we've got a cement, a supplemental cementitious material that can be silica fume as well as other materials. We've got a fine sand, fiber specifically tailored to the application, and then superplasticizer and water. So notice there are no coarse aggregates, since that can interfere with the function of the fibers and compromise the strength of the composite that we're going for here. And there's also no air entraining agent included in UHPC, and I'll get back to that, at least in most UHPCs, and I'll get back to that later also. So ultimately, how does it behave? Well, UHPC is characterized by an ultra-high compressive strength, but also high pre- and post-cracking tensile strengths. And then beyond that, there's due to the high density and discontinuous pore structure, we've got a significantly enhanced durability possible with this material. So the two types of performance that really make UHPC different from concretes that have been used historically are these last two, the tensile strength and the durability. I'm going to get into each one of those individually here. So what do I mean by tensile strength? Well, and how is UHPC different from conventional concrete? Well, first of all, UHPC is stronger in tension, which can actually be evaluated based on flexural testing, which is the basis of the curve that's being shown on the right of the screen here. But the concrete is stronger in tension to the point that the tensile capacity can be relied on in the design of structures. For conventional concretes, we discount tensile performance, but for UHPC, we can consider it. Beyond that initial strength, the material actually becomes stronger after it develops its first crack, because the high strength fibers bridge those cracks and carry those tensile forces across the crack. When you get more fibers mobilizing, that eventually will lead to the ultimate maximum load that concrete can carry in tension. But then even after we get those cracks, the fibers hold those cracks together, absorbing energy as the UHPC continues to deform. And the area under the curve represents that energy. The area under the curve in this kind of a plot. So you can see how much larger the blue area is, representing the UHPC toughness compared to the red, which is a conventional concrete. And here's an example of the tensile performance in action. This is a UHPC beam that was loaded to failure. And you can see along the crack that developed all the fine multiple cracks as the fibers mobilized the material. As I mentioned, the other important property that separates UHPC from other concretes is its durability. So here are some examples. You may be familiar with the Treat Island exposure site in Maine. This is a tidal area that's been used to evaluate all sorts of concrete over the years. But there were some samples of UHPC that were located there. The samples see 100 freeze-thaw cycles per year and tides of 20 feet. They were definitely seeing freeze-thaw cycles through 15 years or so, and there was really no degradation of the material over this period. And again, I mentioned earlier that we don't include air entrainment typically in UHPCs, but they do have this ability to resist the freeze-thaw distress as a result of its high strength and the low porosity that keeps the moisture from moving through the material. The other property that was evaluated in these UHPC mixtures at that Treat Island site was chloride ingress. Chlorides, as most folks are familiar with, I'm sure, are one of the main causes of corrosion of concrete. And so the more resistant to chloride ingress the concrete is, the more durability that can be achieved. So what's shown here in this figure are chloride profiles of a high performance concrete. Those are the blue lines. And compared against the chloride profile, that is the amount of chloride penetrating through the depth of the concrete for UHPCs. That's the orange and gray line. And so what you can see is even for that high performance concrete, which was a pretty durable mix in and of itself, a water cement ratio of 0.33 and still 8% silica fume, over that time period, chlorides were able to penetrate to a depth of about 20 millimeters. In a similar duration, the gray line there, you can see that very little chloride is penetrated past about 7 millimeters. So let me take a step back then and compare typical properties of conventional concrete and ultra high performance concrete. First of all, the compressive strength. For UHPCs, the strengths that we're looking at are generally more than 17,000 PSI. Some definitions set that limit as over 21,000, and values up to 25,000 PSI have certainly been achieved. What that means is that structural elements that are loaded in compression can be significantly thinner and carry just as much load as conventional concrete. Tensile strength of UHPC, as I mentioned earlier, is something that can be relied on for design in UHPC, where generally for conventional concrete, we just discount it. And what that means is that reinforcing steel can potentially be reduced or eliminated because the material itself is able to carry some of the tensile loads. All right, so those are two areas where UHPC is significantly better than conventional concrete. Shrinkage is an area where actually the performance of UHPC is perhaps not favorable compared to conventional concrete. And really, a primary contributor of cracking in concrete structure is shrinkage if that shrinkage is restrained. One of the side effects of eliminating the aggregate and reducing the water cement ratio in the UHPC is a greater tendency for that concrete to shrink compared to conventional concrete. However, since most of the shrinkage in the UHPC occurs at early ages, in some settings, especially, for example, precast concrete, that can be accounted for in design, and so perhaps doesn't have the negative consequences as one might fear. All right, from a durability perspective, I talked about chloride ingress a little bit before. The chloride diffusion coefficient is a testable, quantifiable value for how well that concrete resists the ingress of chlorides. And what you can see by looking at these numbers is the chloride diffusion coefficient of UHPC is about 2 orders of magnitude greater than, smaller than conventional concrete, which basically means there's about 100 times greater resistance to chloride ingress with UHPC, obviously beneficial from a durability perspective. Testing the freeze-thaw resistance of UHPC, what we see is that the relative dynamic modulus after 300 cycles in the ASTM C666 test procedure, which is basically a rapid freezing and thawing cycling procedure, we get very little degradation of the UHPC. A perfect performance in that test would be 100%, and generally what we get with UHPC is 95% or better. Compare that against conventional concrete, where after a similar number of cycles, we're generally seeing about 75%, meaning there was significant degradation experienced by the material. So far I've been talking about UHPC as if it's just one thing, but UHPC is really a class of materials that comes in a number of different varieties. These can really be grouped into prepackaged materials and local material-based mixtures. So an obvious example of a prepackaged material is ductile. That's a material that has been commercialized by Lafarge. Essentially what that is a set of materials that have been pre-selected and combined before they're shipped out to the job site. The advantages of this approach is that the supplier providing the prepackaged mixture can be more selective in the choice of the raw materials that they use. and there's a certain level of consistency in the batching process that can be assumed. Another benefit of the prepackaged materials is that there is a reduced batch time associated with their use. One of the disadvantages of the prepackaged materials is their high cost. And so this is one of the reasons that there's been interest in recent years, especially in looking at locally sourced materials for use in UHPC. An advantage of the local material-based mixtures is that the materials can be selected to be conducive to production based on the local process, but they can also be tailored to the specific project needs. For example, depending on the design and the use of the materials, you might not need a particularly high compressive strength, and you can focus on, say, 18,000 PSI compressive strength is sufficient for your needs. But one of the consequences of the use of local materials is, one, obviously you've got to have a certain level of local expertise in order to produce the material successfully. And then in addition, because it is a new mix design, logically there's a greater amount of verification testing that's needed before it can be applied. Whereas with the prepackaged materials, there's a certain level of confidence on how that material is going to perform. With local materials, that performance really needs to be verified. And I should say again, the local material-based kind of approach is something that is growing in interest around the country. And WJE has actually been part of a number of projects where we've worked with individual groups, precasters especially, looking to develop mixes based on their local materials. With that, I'll turn it over to Elizabeth to talk a little bit about UHPC mixtures.
All right, thank you, John. So John talked a lot about the specific performance characteristics of UHPC, the high compressive strength, the post-cracking tensile strength and ductility, and the high durability. So we're going to dive in a little bit deeper and talk about where does that performance come from. One thing that obviously is going to contribute to some of that high performance is the ultra-low water to cement ratio of the UHPC. As John mentioned previously, UHPC is typically batched at water to cement ratios of 0.2 or less, which is even off the chart that I'm showing here in this figure. Naturally, at those low water contents, you're going to see significant benefits in terms of material performance and compressive strength in particular. It also comes from the use of supplementary cementitious materials, or SCMs, in particular silica fume, which is a very fast reacting material. The silica fume and other SCMs that are present can produce additional hydration products that make the concrete denser, make it stronger, make it more durable. As John alluded to as well, the fibers are going to contribute significantly, in particular to the ductility and post-cracking strength of the material. But really what comes down to is the performance of UHPC is going to be based largely on an optimized packing of particles. We're talking about making the material as dense as possible, and so we need to be able to fit particles together from all different size ranges, with the aggregates, the fine aggregates being some of the coarsest materials in the system, all the way down to silica fume being the smallest material in the system. When you have that dense packing that comes from having this optimized gradation of particles, not only do you get high strength and high durability, but surprisingly, you also get high workability. And that's because if you look at this figure I'm showing here on the right, when you have a lot of particles together, you don't have as much water that gets trapped in between them. That water is freed up to help lubricate those particles. So you actually see a little bit of benefit with respect to workability or flow properties as well. So we're going to talk a little bit more specifically now about some of the materials that go into UHPC. Again, these are very similar to the materials that you'll see in conventional concrete, but there might be a little bit, a few differences here and there. So typically UHPC is going to consist of a Portland cement. We, at least at WJE, have worked with UHPC mixtures that contain type 1 cements, type 2 cements, type 3 cements, even white cements. So there's a lot of different cements that can be used successfully in UHPC. Primarily, it's going to have silica fume. Almost every UHPC mixture currently being developed has silica fume, though there are a few exceptions. The silica fume is really important because it's going to be the finest material in that system. And so if you're trying to get a very dense system, you need to have a very fine material that can fit in and fill those pockets between the particles. It'll also contain a supplemental material. And notice I'm not calling this a supplemental cementitious material, but a supplemental material because it doesn't have to be reactive. Some of these materials might include a silica flour, which is a non-reactive material, or it may include a fly ash, which is reactive. The purpose of this material is going to be to facilitate that particle packing, not so much that it's going to react to form hydration products. The UHPC will also consist of a fine sand, no coarse aggregates. It'll have those fibers. Fibers will typically be steel fibers if you're using them in a structural application, but they can also be polymeric fibers if you're using them, for example, in an architectural application where the appearance might be important. You don't necessarily want to see small little corrosion spots where the steel fibers are very near to the surface. So there are different fibers that may be used. And also certain polymeric fibers can provide fire resistance as well. And finally, the UHPC is going to consist of superplasticizer. These are typically polycarboxylate materials. So these are very efficient superplasticizers for materials that contain high volumes of powder material. And you'll use them at several times the dosage that you might actually see in conventional concrete. What this superplasticizer does is it facilitates some of the workability properties of the UHPC and makes it a very flowable material, even though it has a very low water content. And as John mentioned before, these materials can be prepackaged or they can come from local sources. And so there's going to be some differences in the consistency of the materials that may be present if you have a prepackaged UHPC versus a local sourced UHPC. When it comes to proportioning UHPC, there's no unique mix design. I can't just pull a mix off the shelf and say this is going to be a UHPC. It might not even work. And the rule of thumb guidance doesn't apply. And the reason for this is because, as I mentioned before, the performance of the UHPC is dependent both on the chemistry of the material, so the cement's chemistry, the chemistry of maybe a fly ash that's in the material, as well as the gradation of the particles. And if I change one of those materials out for an alternative, maybe I substitute a sand of one gradation for a sand of a slightly different gradation, my mixture proportions will actually have to change quite a bit if those particle sizes change to account for the difference in particle packing with those new systems. So I'm going to show an example of a UHPC mixture right here. These are proportions by weight. On the left is a conventional concrete, and you can see it's got cement, water, fine aggregate, and coarse aggregate. This is at about a 0.5 water cement ratio. And it contains roughly 600 pounds per cubic yard of cement. So this is what would be called a 6-sack mix, which means it has 6 sacks of contains 6 94-pound sacks of cement. On the right is a UHPC mixture, loosely based on the proportions of ductile, though not entirely the same. And what you can see is that the total amount of cementitious material in these mixtures is actually quite different. On the left, in the conventional concrete, the cementitious materials make up about 15% of the material's weight. In the UHPC, it's closer to 45%. So a lot more cementitious content in this mixture. Otherwise, the material proportions are actually fairly similar with respect to the water, which is about 7% in both mixes. And the aggregates, the fine aggregates, which are about 35 to 40% for both mixtures. Effectively, what the main difference in proportions is where the conventional concrete is going to have coarse aggregate, that entire weight is substituted with fibers and additional cementitious material. So I mentioned that this conventional concrete mixture might be what's considered a 6-sack mix. If I did the same math for a UHPC mixture, it would be a 20 sac mix. So now I'm just going to show the numbers that are associated with those graphs. I know some of you are probably more number people and others are graph people. So just to compare the numbers a little bit, the conventional concrete has 600 pounds of cementitious material. That UHPC mixture, by comparison, has over 1,900 pounds of cementitious material. And then that water to cement ratio or water to binder ratio that I'm showing, because there's so much cementitious material in this mixture, our water to binder ratio is going to be less than 0.2. So now let's talk a little bit more specifically about how we actually develop these UHPC mixtures, with particular attention to local materials, since that's what John and I have worked with quite a bit lately. So there's a few different approaches to developing UHPC mixtures. One is to do sequential trials. So what this would be is, say I've developed a mix design on paper and I test it out in my plant or in the lab, and I see, is the workability where I want it to be? If it's not, well, maybe I want to change the proportions of my sand, maybe reduce some sand, add some cement, add a little bit more water, change my super plasticizer. Essentially, batch a mix, see how it performs, make a few iterative adjustments, and then batch again until we get a mixture that performs the way you're looking for. There's also experimental design methods where if I'm looking at a particular group of cements, particular group of supplemental materials, maybe a few different sand gradations, I look at different options from each of those categories and use statistical principles to come up with a matrix of different mixtures that I'm going to make. I make all of the mixtures, evaluate their performance, and then use statistics to figure out, based on the performance of each of those mixtures, which component at which dosage is going to give me the best performance. The third approach, which is one that John and I have used quite a bit recently and found to be very effective, is to use particle packing models. And since this is unfamiliar to most of you, I'm going to do a very, very broad overview of what a particle packing might look like. So one of the particle packing models that John and I have used is called the modified Andreessen and Anderson model. And basically what it does is it looks at the gradations of the different materials. So many of you are probably familiar with a gradation for sand, which I'm showing here on this graph. So what a gradation is going to do is it's going to say for a given size range, I have a certain percentage of my material that falls into that size range. Well, we can get the same information for our cements and our silica fumes and for other powder materials as well. Then when we combine those materials in certain ratios, we'll get a combined gradation that represents all of the sizes in that combination of the materials, all the way from the finest material, which is probably going to be mostly the silica fume, up to the coarsest material, which is going to be mostly the sand. Once we have our combined gradation, we're going to look for a target gradation that's going to be defined by our particle packing model. What we're trying to do is adjust those proportions so that our combined material is as close to the target as we can get. So for this example, I have a little bit more coarse material than I want. So maybe I'll reduce the amount of sand that I have in this combination and increase the silica fume. Maybe I'll get this combination. Well, this one now is a little bit too fine, so I'll adjust again. And now I'm very close to that curve. These proportions are going to be close to what I want to work with. And so then I'll play around in the lab or in the plant and try different water combinations, different admixture combinations till I get the performance characteristics I'm looking for. So when I'm developing a mix, here's a few of the performance characteristics I might consider. Obviously, the compressive and tensile strength, the durability that we've talked about, the long-term material availability. Do I have a particular material that I'm concerned isn't going to be available for the duration of a particular project I'm working on? That's a factor that might be considered. Workability and workability retention. How flowable is this material? Does it have self-consolidating properties And how long does it stay self-consolidating? How expensive is the mix going to be? What's the cost? And also, what are the production capabilities at the plant? Do I have enough silos at the plant to handle an additional supplemental material, for example? So just to give you an example, if I'm developing a mix design, I might consider the ones I've highlighted first. I might consider compressive strength, workability, cost, and production capabilities to make my initial selection. But once I've developed a mixture that I'm happy with that meets those 4 criteria satisfactorily, then I'll look at the other ones and do additional evaluations to make sure that my mix is going to work long term. In terms of characterizing the UHPC performance, I did talk about workability and workability retention, and this picture is performing a flow test. So UHPC is self-consolidating. It'll flow under its own weight. And we perform a flow spread test that's very similar to what's done maybe with self-consolidating concrete, except it's done with this small little 4-inch cone, so it's a much smaller scale test. We can also measure the temperature of the UHPC. John will talk later on about how temperature is very important when it comes to long-term workability. So temperature is very important. And also setting time, which is good to know for a lot of production applications. In terms of mechanical properties, we can characterize the compressive strength and elastic modulus of the concrete. We can characterize the flexural and tensile performance of the UHPC. This is a picture of a flexural test that we've performed in our lab recently. And then we can also characterize the creep and shrinkage performance of the mixture. These are properties that are going to be very important when it comes to design with UHPC. And WJE is now accredited to perform all of these tests under ASTM C1856, which is a new standard that defines testing procedures for ultra-high performance concrete. And finally, when I think of ultra-high performance, I think of performance, I think of durability. And so for UHPC, it's often also important to characterize the durability. And so this can be accomplished through characterizing the absorption, which reflects how much moisture can be absorbed by the concrete. It can be performed by assessing the chloride penetrability, either through a rapid chloride permeability test or RCP test, which a lot of DOTs specify, or it can be accomplished through a diffusion coefficient test, which is probably a little bit more accurate for a material like this that's got a pretty high density. And finally, you can characterize the freeze-thaw resistance, which I'm showing in this figure here.
All right, so I'm going to come back in now and talk a little bit about the production of UHPC. UHPC can be produced generally using similar equipment, same forms, for example, as conventional concrete, but there are some additional areas that need to be considered. Obviously, materials acquisition and handling may be a little bit different if we are talking about different raw materials than conventional concrete. The charging sequence of the mixer, especially handling the fibers, is something that's a little different. Batching controls, 2 important components for conventional concrete that are even more important for ultra high performance concrete are moisture and temperature. And then placing, finishing, curing are all handled just a little bit differently. And I'll get into each one of these here. So first of all, let's talk about the mixing process. Generally, it's a slower process than with conventional concrete, but it starts with blending the dry materials. So if you can see the video working here on the right, generally what we start with is putting the dry materials in the mixer, get those to be homogeneously distributed, and then we add the mixing water and the admixtures. The concrete is then turned through the mixer, and what starts to happen is the material starts to ball up into dry balls, first of all, and then they start to get this almost like bread dough consistency. And then eventually the material turns. And turning is the process where it kind of goes from a dry material into a fluid state. And as Elizabeth alluded to, the goal here is to really get it to a self-consolidated consistency. And if you can see in the video there now, we've got that kind of nice liquid uniform condition. And typically, it's at this time period that fibers are added to the material. There have been as a means to speed up the process. There have been attempts to add fibers earlier in the process, and that can be successful as well. But again, the more typical process is to wait until you get that fluid consistency before adding in the fibers. So what I showed you was production happening actually in the horizontal twin shaft mixer there on the right. But UHPC can actually be produced in most mixers. The difference is just how much time it takes to get that material to turn and reach that fluid state. So it can be produced in a pan mixer, and then even in some cases, it's been produced in a regular excuse me, mixing truck. The duration of that mix will be influenced by that mixer, as I said, but in general, another thing that influences how long it takes to mix is kind of your approach to the mixing process. If you're starting with a pre-bagged mix, for example, looking at a small batch that's batched on site, you may be able to get the mixing done in 5 to 10 minutes. But if you're looking at a larger batch, for example, at a precast plant, whether you're working with pre-bagged materials or non-pre-bagged materials, it might take you 10 to 20 minutes. Production, as I said, moisture and temperature are two important issues. You know, the amount of moisture that's included in the UHPC is critical to make sure we maintain that low water cement ratio. So while it's typical for most conventional concrete production to consider the amount of moisture that's in your sand, for UHPC, you also need to consider the amount of water that's introduced into the mix by your superplasticizer. This is also because there's a lot of superplasticizer in UHPCs, and superplasticizers are often as much as 60% water. So that's something that we need to be careful about. Other thing that we need to be careful about in order to maintain our workability is controlling the temperature. Ideal concrete UHPC temperatures are lower than typical concrete temperatures. Really, the target range you want to get is 50 to 80 degrees Fahrenheit in order to maximize long-term workability for most UHPC mixes. And so sometimes that requires introduction of ice as a substitute for the regular batch water. The UHPC is typically self-consolidating, and so it can be placed and handled in ways that one typically does with self-consolidating concrete. However, the mix, because of that silica fume and the low water cement ratio, it does tend to be a little bit sticky. And so it just takes a little bit longer for that self-consolidating process to happen. Vibration of UHPC is generally a bad idea. That's because especially internal vibration will disrupt the distribution of the fibers. And external vibration, for example, in a precast plant, if the mix is not stable, could promote segregation of those steel fibers. Another important consideration in placement of UHPC is that the concrete really should be placed to avoid cold joints, avoid lift lines. And that's because if there is a cold joint, that introduces potentially a plane that fibers don't bridge across. So remember that we're relying on those fibers to provide that tensile capacity. And if you've got a zone where there are no fibers, you've got a potential plane of weakness in your material. Because of the small amount of water relative to the cementitious and the powder materials that are in your UHPC, it can dry out very quickly. Finishing UHPC is a little bit tricky too because of that stickiness. And so really what you want to do is finish it quickly. And then as you see here, perhaps use a roller as opposed to an ordinary float or trowel to finish the material. And then you want to protect those surfaces as quickly as possible with plastic sheeting. That will help slow any of the plastic shrinkage cracking that can occur with UHPC in windy or hot conditions. Once you've got your product placed, your concrete placed, there are two common procedures that are used for curing. Historically, with some of the UHPC materials on the market, the recommendation has been to apply a post-cure thermal treatment. So the concrete's allowed to cure at least through 2 days, and then it's heated up to 190 degrees for 48 hours using steam. And there's some benefits to that we'll talk about in a second, but that's in comparison to regular ambient curing where the concrete's just allowed to cure. I should say that ambient curing does provide, through heat of hydration, some significant temperature typically with UHPC, and that's beneficial from a strength perspective. So just to touch on some of the benefits of that post-cure thermal treatment, it helps encourage the development of strength, and often you'll get a strength that exceeds the ambient cure. Most of the shrinkage is complete after that treatment. It kind of locks in the dimensional stability of the material. By contrast, the ambient curing, you will expect that UHPC to continue to shrink throughout its first few months of life. And as I alluded to earlier, that does have some potential consequences for cracking if it's not handled appropriately. But obviously the benefit of ambient curing is that it doesn't require any special equipment.
All right, so we've talked a lot about some technical information right now. So I'm going to take things a little bit back and talk about some of the big picture uses of UHPC in the current applications. So UHPC is used in two large applications right now in the United States and abroad, primarily in architectural applications and in structural applications for bridge construction in particular. So the first of these applications that is probably more common is in architectural facades. UHPC is used in facades for a few different reasons. The first is that, as we've talked about before, the high strength of the material means that you don't need to have as much material to support the same loads as conventional concrete might be required to support. So you can use thinner elements, lighter weight elements. You can also, because it's self-consolidating, it can fill more complicated forms. So you can get some of these more intricate form and more intricate patterns like I'm showing here in these particular architectural facades. It can also be produced with white cement, so it can be white or colored to suit certain projects' aesthetic needs. It can also be used not just in these showcase projects like the museums I had shown before, but it's also used in facade panels for more conventional construction, residential buildings like I'm showing here on the left. It can also be used for roof canopies and other lightweight thin structures because it's got the high strength of the material and the particular coloring features that you can have. One of the biggest applications in the United States is precast bridge connections. Here I'm showing a picture from the Franklin Avenue Bridge in Minneapolis, where the UHPC is used to fill the joints between precast panels and bridge construction. The reason this is done is because the UHPC bonds very well to the reinforcing steel, and so you don't need as much development length. Or if you have areas where you've got tight congestion because of the reinforcing between the panels, the UHPC, being flowable, can help fill and consolidate well in between those areas. UHPC has also been used on a few projects in the United States for actual bridge elements. Here I'm showing a figure of the pie girder, which was developed by FHWA, the Federal Highway Administration, to take advantage of a lot of the UHPC's properties. But they're also being used internationally for bridge applications. This is a bridge in Malaysia, which is made of UHPC. It's a 100-meter span, so 328 feet, made entirely of UHPC. And this is fairly routine construction now in Malaysia and other parts of Asia to use UHPC in these structural capacities. So the benefits of UHPC are really that a lot of the properties allow it to meet unique project constraints. It's got long life, so it can be used in applications where corrosion resistance or durability is necessary. It has high strength and ductility, so you can use lighter sections, shorten development lengths for structural applications. And because it's self-consolidating, you can create more complex shapes. You can also transfer specific surface textures to the material because it actually can match patterns very well. But there's also some additional considerations. You know, UHPC is not going to be the solution for every project. One of the biggest considerations is going to be the cost of the material relative to the total cost of the project. UHPC is typically pretty expensive, on the order of $1,000 to $2,000 per cubic yard, possibly even more. So those initial costs are going to be weighed against the long-term costs of the project. Can you use this higher cost material because you're going to have reduced need for repairs in the long term, for example? Other considerations are with respect to the size of the element. Large elements, UHPC might be a good option because you can have a thinner, lighter section. But when you have a larger element, you also have the increased potential for higher heat generation during hydration. So you might introduce potential for thermal cracking. You have a higher risk of issues related to shrinkage. On the other hand, when you do smaller components or precast elements, UHPC might be a very good fit there. But also the relative cost of the material might make it something that you would choose an alternative material for, depending on the size of the project. Additional considerations are related to the production needs. If you have a large cast-in-place project, for example, using small batches of prepackaged materials is going to make the process a lot longer and production a lot longer. So consideration of the production related to the project. And finally, the last consideration with respect to UHPC is, do you actually need the performance? If you're making a temporary structure where you don't need long-term durability, UHPC might not be the best choice there. Alternatively, if you've got a structure in a high corrosive environment or a place where durability is necessary, or an application where you are going to be relying on the tensile strength of the material, UHPC might be a better choice over some alternative materials.
All right, so let's talk a little bit about kind of the future of UHPC and where that's going. Certainly, we spent a lot of time today talking about some of the material aspects of UHPC. And one area of growth is the development of more suppliers providing prepackaged materials. In addition, we've talked about local material-based UHPCs. That's been a focus of precasters and even some ready-mix suppliers, and that's been supported by work done by WJ as well as various DOT and universities. The production of UHPC has really been focused on how to make the material more easily, how to make it more quickly, how to make it more consistent. And so that's looked at batching systems, mixers that are particularly well suited to provide the high energy to get the material combined, as well as methods to automate the introduction of fibers into the system. Precasters are also exploring how far they can go with their existing curing systems to see whether that post-cure treatment is really beneficial. And then finally, as it's obviously true that UHPC is dependent on the chemical admixtures, we continue to look at development for retention of the workability as well as potentially mitigating some of that shrinkage that I've been talking about. From an application perspective, there is work underway to develop long span bridge beams. On the right here, you see a cross-section of potential U-girders. On the left side of the figure is a conventionally designed U-girder. On the right is a UHPC. And you can see the wall thickness is significantly reduced with the UHPC, resulting in about a 50% reduction in load. Those benefits can also be applied in building beams. Here's an example of a voided slab where the goal here would be to increase the spans of flooring systems, for example, and eliminate the number of columns that are required on the interior of a building. We've talked about durability a bit here today, and that has applications, for example, in piles. The photo here is a picture of a pile that was cast with UHPC actually being tested at the Florida DOT Structures Testing Laboratory. And here what we're looking at is really, can we achieve through that really low chloride permeability a realistic structure even in a marine environment that's going to last 200 plus years. And I think with UHPC we're really starting to get there. And then finally, with repairs, here's an example of a bridge deck overlay where that UHPC provides a very impermeable layer protecting the underlying concrete. And W's actually also looked at implementation of repairs with a precast cap system to protect an underlying concrete, conventional concrete in a severe exposure environment. I mentioned at the beginning that the availability of specifications was one of the limitations in the implementation of UHPC. And that's true, but it's changing. You know, in the beginning in the United States, much of the UHPC work was based on demonstration projects that relied on project-specific specifications. However, recently, the FHWA has provided updated guidance on field cast connections, and there's a discussion in that tech note that specifically addresses specification of UHPC for that application. Elizabeth alluded to the ASTM standard, and that provides a basis for the test procedures required to be incorporated into specifications. There are also ongoing efforts funded through PCI at the FHWA and at DOTs. The PCI effort is part of a research project that is being led by eConstruct and by us here at WJE, and the goal there is to foster the implementation of UHPC. A major deliverable of that project is a guide specification for the use of UHPC in precast structures. So that's specifying the material. The other part of the implementation of the material is design. From a structural design perspective, there are a number of international standards that outline general design procedures, but to date, there's nothing available in the US. However, that too is also kind of changing. The PCI project I just mentioned is looking to develop guidelines for long span elements for both bridge and building applications. FHWA is working on a parallel track, also looking to develop guidelines for bridges. And in addition, the ACI committee on UHPC is also looking into developing documents to aid in the use of UHPC. So in summary, while UHPC has some significant advantages versus conventional concrete, really the point I try to make as we kicked off this presentation is that it's a natural evolution in concrete. The advantages that make it different, though, are its tensile properties and its durability properties. So while UHPC isn't for every job, structures that can leverage these properties, these advantages, can be significantly improved compared to what would be achievable with conventional concretes. Really what the UHPC can make possible is lighter sections with reduced cross-sectional areas and longer spans, as well as longer life structures. So while we recognize that there's an increased materials cost and effort compared to conventional concrete and the use of UHPC, the capabilities that UHPC introduced ultimately provide a value to the built world here that are not achievable with conventional approaches. So that's our presentation this afternoon. We'd like to see if there's any questions.
Yeah, thank you, John. As a reminder, if you have a question, you can type that into the Q&A box and hit send. And we'll try to get to as many questions as possible before the end of the hour. But if we don't get to your question during the call, John or Elizabeth will follow up with you afterward. So let's go ahead and take our first question. What is the track record for using UHPC for slabs on grade with the goal of eliminating control joints?
Well, generally, UHPC has not been used on slab on grade. The slab on grade concrete is generally, you're looking at a more economic application of material than is achieved with UHPC.
Okay. We'll take the next question. Is UHPC generally heavier than conventional concrete?
So on a unit weight basis with conventional concrete, we might think of it as having a density of maybe 145 to 150 pounds per cubic yard. UHPC is going to be a little bit heavier because of those steel fibers. And we typically see unit weights of about 155 to 160 pounds per cubic yard. So it is denser, but it's not necessarily heavier because you can get away with using less material in your cross section to get the same mechanical performance.
Okay, next question. We have heard that UHPC can be furry because the fibers tend to stick out. What are the strategies for dealing with that from a usability and appearance point of view, and does that add significant cost?
Well, as Elizabeth talked about in her presentation, steel fibers are generally used in structural applications. The potential concern in a severe exposure environment, such as where there's chlorides, is that where the tips of the fibers are in contact with the formed surface, there can be a little local bloom of corrosion product. Generally, that is just a near surface effect, and actually we've seen people that have taken pieces of concrete, exposed it to chlorides, and then cut the very edge off, and all you see is just a very extreme edge, 1/64 of an inch or something, that chloride has penetrated. From an appearance perspective, what can be done is a coating applied over the surface of the concrete, and that protects that underlying concrete and prevents that from occurring. And again, that's steel fibers being used for a structural application. The polymer fibers that are used in architectural applications are generally less objectionable from an appearance perspective, and so are not as much of a concern from a appearance perspective. And that's the reason why that you're choosing to use the polymer fibers, because they do not affect the appearance.
Okay, next question. Is the orientation of fibers critical to the tensile strength? Do they end up oriented in all directions, or are there precautions taken to ensure fibers end up in a certain orientation? Also, would you typically utilize rebar in a UHPC design, or do fibers typically eliminate the need?
Well, I'll start by answering this, and John might follow up with some additional comments. But UHPC, because it's so flowable, the fibers are going to follow that direction of the flow. And so they tend to be oriented the same direction that the material flows through the form. This can be used advantageously in certain designs. For example, if you're going to cast a member that you know is primarily going to be loaded in a way that the fibers can help resist some of the tensile forces, you might make certain production choices in how you cast the material. But in other cases, it might need some additional considerations. In terms of the use of tensile reinforcing, currently the trend is to reduce the amount of tensile reinforcing steel in UHPC, but not to eliminate it entirely because of considerations of fiber alignment and cold joints, etc.
Okay.
Let's see, we got time for maybe one more.
Yep, let's do one more question. Okay, can you get a broom finish on UHPC, or does it set up too quick?
Yeah, as I alluded to in my earlier discussion, the finishing of UHPC can be tricky because things do happen very quickly. Generally, getting a traditional broom finish is not possible. What may be attempted if you're looking to get a particular finish on the surface is to actually think about casting, especially if it's a precast element, is casting things upside down and use form liners in order to achieve a particular surface condition.
Okay, thanks, John. And thank you both for your presentation. That's all the time that we have for questions today. We'd like to thank all of you for joining us. We hope it's been educational. And as a reminder, we will send an email to you with instructions on how to receive credit for participating in today's webinar. And that email will also include a recording of the webinar for you to share with colleagues. So again, we really appreciate your time, and we hope you have a great rest of the day.